Yeah. We had this idea last day that if I pushed a magnet into a solenoid, I could induce a current. And so we're still carrying on with that idea. But one of the things we said was that when we have an electromagnet, if you run more current through it, the magnet's stronger. Another thing we said, when you have an electromagnet, a solenoid, if you have more coils, the magnet's stronger, right? And so when I look at this, it's also true for generators. When I have more loops, we end up getting more current. We don't just get more current, but we get more voltage. Now, current is a flow rate. Current is number of, it's measured in amps, but it's the number of coulombs flowing through a section of the circuit per second. It's coulombs per second. It's a flow rate. Whereas voltage, it has units of volts, this electric potential, but what it really is how much energy you give per unit of charge. So it has units of joules per coulomb. In other words, if I got more coils here, I'm going to be firing that current through the circuit faster, and I'm going to give more joules per piece of charge, right? And that kind of makes sense too. Like if I shoot a ping pong ball out of a ping pong ball gun, it's going to have a slow rate of motion. But if I take a, golf ball machine gun, it's going to have higher rate of motion, but also more joules per golf ball, right? I know that sounds like the stupidest thing ever, but I'm just thinking about like similar little white balls, right? So like that's all. We're just firing electrons faster and harder through this circuit if I have more coils. Another thing that we could say, if I want to be kind of equation-y about this, is that since there's more current and there's more voltage, there's more power. Now, quick little aside about power. It corrupts, absolutely. But it also is equal to voltage times current. Okay? Well, how do we know that it's equal to voltage times current? Well, I just wrote this equation. V is equal to delta E over Q. I'm using capital Q, sorry. I also know that current, so I'll like put a little arrow to that voltage. I also know that current is equal to the flow rate of Q charge that flows through a circuit in a certain amount of time. So delta T, the amount of coulombs that goes through a circuit in a certain amount of time. And if I put those two together, if I sub those two equations that are not in a box into the equation that is in a box, then what I get in this box is power is equal to delta E over Q times Q over delta T. And it doesn't take a lot of thinking to see that the Q's cancel out, and I end up getting power is equal to delta E over delta T. See what I'm talking about? So these are two sensible equations. If you know what voltage is, it's the amount of energy per charge. And if you know what flow rate is, it's the amount of charge that flows through per second. And we whack them together into this little formula. It kind of proves for us that it's power is V times I, okay? Just because it fits with our definition of what power is. Delivery of energy per second. So maybe we'll write this off as a little equation for ourselves. Power is equal to delta E over T. That hasn't changed. I'll put a box around that because that's important. V is equal to delta E over Q. I is equal to Q over delta T. Those are four nice equations. They should show up on an equation sheet somewhere. They're things that we should know, okay? All right, so back over to this thing. The induced voltage, and I'm saying voltage as slang. We all know it means electric potential difference. It's just Volta's last name, kind of messed with. The induced voltage is proportional to the product of the number of loops. So now we're back to my picture again, off the equation for a second. And the rate of change of B. Just give me a second. The time rate of change of B. Now, maybe that needs to be unpacked. What does it mean to have a time rate of change? I think that most people would understand better if I didn't phrase it as the time rate of change of B through the loops, if I rephrased it as the wiggle rate of the magnet. Doesn't that sound more understandable? The rate at which the magnet encounters that wire and wiggles back and forth. So the faster I shake it, the more energy I give it. And that kind of makes sense too if the current that's in this wire is really experiencing motion because of an action-reaction situation. The more I push on this thing, the faster I push on this thing back and forth, the more I'm going to get that current wiggling around, right? So faster I wiggle it, more energy delivered. Now, there is also a proportionality. This is the alpha symbol, proportional to, so let me write it in handwriting in case that's kind of obscured for you. The voltage is proportional to, therefore, the number of loops times the cross-sectional area I'll put that in brackets because it's a sort of a word statement, times how fast I wiggle B, how fast I wiggle the magnet. All right. Now, if I wanted to steal something out of a textbook, I've left this like willfully crooked and obviously screen captured. Can you see this definition? A lot of times I'll take the time to retype it. But I left it like this to remind me that this is the actual textbook definition. I can see that I copied and pasted it right out of a textbook, right? So not a lot of things that I leave that way. That one there is so you guys can see it's the textbook definition of the law of electromagnetic induction. Classic. Okay. There's a quick little thought bubble here. It says, it's more difficult to push a magnet into a coil with more loops because the magnetic field of each current loop resists the magnet. That's that action-reaction thing, right? All right, so using induced current to perform tasks. We want to actually have a practical application for this. So not only can a magnetic field, a B field, create current, but that current can be used to make another B field. I think that kind of makes sense, actually, but I want to use the diagram to the right as an illustration tool. Make another B field elsewhere. And I want to follow this current diagram at the side. So in this situation, I've got this hand, and this hand is pushing a magnet into a solenoid. This is the action. I'll write a big F there for force. Now look at the windings on this. Notice that it winds to the left in the foreground, and it winds, what did I get that right? Yeah. It's winding to the left in the foreground here, winding to the right in the foreground here. You guys see that with the three-dimensionality of this? And you can see that this textbook even borrowed the same kind of thinking of using like a toilet paper roll for a core, right? Like just to show the three-dimensionality of what's going on here. If I shove this north in, remember, the solenoid is going to resist an incoming north. So that means that the top of this, I'll put it here in the shiny spot. The top of this solenoid is north, resisting the incoming north. Use your right hand. Is the current going into the page or out of the page along the right-hand side of that solenoid? How many people say out of the page? If you did, you're wrong. Because it's into the page, right? Okay, good. I like these looks of like, no, did I do it wrong? Okay, so it's going to go. I just say the wrong thing and then do the wrong thing? Into the page. Into the page. All right, dots are turned into X's quite easily. That's okay. That means it's going to come out of the page on this side. So I'm just showing what's happening inside those wires along the edges of that solenoid. But if it's going to go out of the page on the left and into the page on the right, doesn't that mean that in the foreground, the current has to be going that way at the top, and in the foreground, the current must be going this way at the bottom? So we got to think about what's going on three-dimensionally with this, and we just carry on, carry on the labyrinth around the pathway. Notice it wraps around behind the second solenoid and comes into the foreground. I'll go over and draw my arrows in the shiny area so you guys can see. It's traveling to the left in the foreground. It's going to go into the page on the left-hand side of that solenoid. which means it's coming out of the page on the right-hand side of this solenoid. And then it carries along through what looks like some sort of an ammeter or multimeter or something like that, just to say the current does have a flow direction. Okay, so let's label this up that this is an ammeter. And yeah, that's how you spell ammeter, with 2 M's. Anyway, as I look at this, the claim was that I could use one magnetic field to induce a current, but I could also use that current to produce a magnetic field elsewhere. And you can see what I'm talking about now, right? So I look at this guy over here, and which end is the north end? Use your right hand again. Do we all agree that the bottom's north? All right. This ends up being north then. That means that this is the south end of that solenoid. And so people say, well, what would we do with this? Why would you care to do that? Why would you want to send a magnetic field somewhere else? It turns out that this is basic telecommunications using electromagnetic induction. Think about this. If I were to take another bar magnet just sitting on a tabletop, here's my bar magnet, and I let the north end be facing upwards and the south end be facing downwards, you can imagine that if I went like, and I put like a splotch of glue on the bottom of that bar magnet, and I pasted it to a piece of paper. Oh, little drip on the side. Oops. Anyway, I attached it to a piece of paper. When I shove this magnet in on the left-hand side of this system, can you see that that's going to induce the north on the secondary solenoid? And we call it the secondary. Maybe I should call that secondary because it came second. You want to know what the first one's called? Primary, yeah. Just like in school. Okay, go figure. The primary and the secondary. But what that means is that when I shove in this magnet over here on the left-hand side in the primary, the magnetic field induced in the secondary is going to do what to this bar magnet? Attract it or pull it? Or push it? Attract or push? Come on. Everybody together. Push. It's going to push, yeah. All right, so that means that I'm going to end up getting a force on that magnet. Now, people that did a sound and waves unit, can you guys see how this is actually a speaker? Isn't that paper going to bump into the air in front of it? You guys see that? This is a telecommunications speaker system. And the truth is, this hand doesn't have to be what's forcing it. Would you believe that I could somehow mount a piece of paper on the top of this one? And instead of having a hand wiggling this thing up and down, I could have somebody talking at that piece of paper. And when I talk at that piece of paper, that would wiggle this magnet up and down. I'd have to have it in some sort of properly mounted system. I mean, maybe I could like add springs to the side and have like some sort of a framework, you know, like a cylinder where it was side mounted to springs, where it was allowed to bounce up and down. And like maybe on the top of this setup, mount, you know, maybe it'd be like a can. And I could put a piece of paper on top, glue this magnet to the piece of paper, and have it like spring mounted to the sidewalls. Can you imagine that that's now a microphone? Am I selling this idea? This thing vibrates up and down, and whatever rate it vibrates up and down, the current is going to get pushed one way or the other way in this primary solenoid. And whatever direction this gets yanked back and forth is going to result in a north-south polarity flip in the secondary solenoid. That means that the rate at which I wiggle this guy up and down is going to be the same rate at which my secondary solenoid wiggles what's now our speaker up and down. And of course, that means that that's going to cause compressions and rarefactions, you know, high density and low density regions in the air beneath that paper. And that's sound. This is karaoke. True? And people say, okay, well, how could you make it be louder? Oh, well, let me tell you. I could make there be lots of windings, right? That sounds great. I could play around with how strong the permanent magnets are. Sounds great. And in fact, if you ever look at a speaker system and dissect a speaker, the magnets inside of a speaker are freaking strong. Sorry for the F word, but real, right? Like they are strong magnets. In fact, as a kid, I can remember destroying my first speaker. I threw a speaker at the ground. It was in a garbage area. There was I don't know how to say that I was a dumpster diver or anything, but I saw this speaker and I wanted to know what was inside. And it was a great big, you know, those dumpsters, right? Great big speaker inside a dumpster. And me and my friend Kevin, we smashed the speaker on the ground. I don't know whatever happened to Kevin, but he's gone elsewhere. Never heard from him again. I think he's selling cars somewhere in another part of the city. But we smashed that speaker and we got some really powerful magnets out of it. And what we learned was that, first of all, they're powerful, but also if you throw them through the air, they'll stick to the side of a dumpster like magic. And they'll like take a left turn if you just miss the dumpster, and they'll stick to the side of that dumpster. That's how strong they were. We were just, as kids that grew up reading Marvel comic books, we were like, oh, I'm Magneto, like that was amazing. All right, so we got this idea of strong magnets being something that's key to a speaker system and telecommunications. Of course, you can scale this thing down, and you can put those magnets into something like your what's the fruit-based phone company? Apple, yeah. And then they got those the buds that you stick in your ears. What are they called? Yeah, those ones. They also have this kind of system set up on a very small scale, right? That's what the speakers are inside of your ears. Of course, the signal gets sent wirelessly for those, but the speakers still work. Anyway, transformers, they are more than meets the eye. And we want to talk about the fields inside of these things. I'm going to switch over to another color because that color is dying on me. Fields from current produces current from fields. And so the last little thing we talked about was about communications. This is about power distribution.